Hello, everyone. Welcome back to the AAS YouTube channel, and this is part of the great stuff. This is the AAS Journal Author Series, and I am super happy to have João Amarante with us today.
Yeah, thank you for having me, Francis. Thank you for the invitation.
Well, thank you so much for agreeing to talk about your very lovely article. I think it's great.
Yeah.
And João, where are you located at?
At the moment, I'm at the University of Edinburgh, visiting a collaborator. But I'm based on Barcelona as a postdoc, and working with Dr. Sherwin Laporte also. So it's quite cool. And yeah, and what about you?
Yeah, I'm doing super duper. I'm in Phoenix, Arizona. It is October 24th, 2022, as we shoot this video. And fall has finally arrived in Phoenix.
So and how's the weather there?
The desert's now cooling off. So we are, let's see, we're at about, we were at 52 Fahrenheit this morning. So what, 17 C, something like that?
Okay,
so real quick. It's a little on the cooler side for the desert, but it's certainly a lot warmer than, let's say, maybe in Scotland.
Yeah, and maybe drier, because here it's raining all the time.
No, we're still a desert. We're still quite dry. Yeah, very cool. And so you go back to Barcelona in a couple of weeks?
No, actually this Friday. So I arrived here last week, and just 2 weeks as visiting here to increase the collaboration with one of my collaborators.
Well, then you get to go back to Barcelona, which is presumably a little drier and a little warmer.
And more sunny. Yeah, it's always sunny in Barcelona, actually.
I'm going to have to visit there because I like really sunny places. So
yeah, it's sunny all the time. It's very, very good.
Very cool. Very cool. And João, what do you like to do for research?
Yeah, so I mainly study the structure and evolution of our galaxy, the Milky Way.
Cool.
And the way I do it, it's with simulations. So with tailored simulations of our galaxy. And I compare the simulations with observations and try to understand then the process that originated our galaxy and how it evolves.
Awesome. Very nice. And that is going to bring us to this very awesome APJ article, Gastro Library 1. The simulated chemodynamical properties of several Gaia sausage Enceladus-like stellar halos. And João, take us away.
Yeah, so again, thank you for this opportunity. And I also want to mention my collaborators on these papers, the co-authors. So Victor de Batista, who is based on Preston in the UK, Leandro Beral de Silva, who is a former postdoc from Victor, but now he's based on Michigan, Sherwin Laporte, who I'm working with in Barcelona, and Nathan Degg, who is also a collaborator and based on Canada. So yeah, it was a very
international grouping here.
Yeah, international grouping, and everyone worked hard on this project, so it's quite cool.
Nice.
So yeah, so the idea of this this paper of this Gastro library that I'll be talking soon is to investigate these properties of the stellar halos that formed in a merger that we think it happened in the Milky Way. And this name, Gaia sausage Enceladus, this weird name, sausage in Enceladus, yeah, we don't need to talk about the naming,
that's a whole
but anyway, so it's a dwarf that merged with our galaxy in the first 3 giga years, of the Milky Way, and then it left several imprints in our galaxy. But before we go to that, then so we know, like there is there in the introduction, that we know that our galaxy, it's a kind of common galaxy in the universe, so it's a disk galaxy, and the process formation of these galaxies in this lambda CDM scenario is that it happens through several mergers or minor mergers. Yes. And then these minor mergers, they are going to build up the stellar halo of these galaxies. And then in our galaxy, the Milky Way, we already know that there are several either streams that are remnants of previous mergers. So these are seen beyond 30 kpc from the galactocentric radius of our galaxy. So these are distant, very distant substructures. And we can also observe like things, dwarfs is still interacting, that's probably going to merge in the future, like the large Magellanic clouds. In Sagittarius and so on. But within this 30 kpc, so closer to in the inner parts of our galaxy, we also kind of can identify previous possible mergers that happen in our galaxy. So people have done this, are doing this still, and especially now with the Gaia data, which provides promotions and parallax for the billions of stars. So we have a very good, precise 6D phase space properties of these stars. And then we can identify probably substructures in this Milky Way interstellar halo. And the main idea behind that is that when a merger happens with a small satellite, the stars that are created, they are going to be kind of clumped in this energy angular momentum space. So one can basically try to argue that if different distinct mergers, they are going to be in different parts of this energy angular momentum space. So if you can identify different substructures in this space, you can say, okay, you have 1 or 2, 3 minor mergers, right? And then you can go to the next page, for instance. Sure. So that's the main idea. And now back to this Gaia sausage Enceladus, we for over 2 decades, basically, we had hints that our galaxy, when it was young, it had a major merger that happened. And major mergers in the sense that on that time, the galaxy or the dwarf galaxy that merged with that had a comparable mass, or at least 10% of the mass of the Milky Way galaxy on that time, at that time.
Okay. Yeah.
And then with the Gaia data, these little hints that we had from previous works, like for over 20 years, it just became too evident. Like we could clearly see the signature of this major merger. And then that was basically it was identified by 2 different groups, basically at the same time. So that's why it has this Gaia sausage Enceladus name. And sausage, we will understand later, there will be in one figure. It's because due to the nature of its merger, which was in a very radial orbit, the accreted stars end up having a very anisotropic velocity distribution, which means that the radial velocity dispersion is much larger compared to the rotation velocity dispersion. So we can actually jump to one of the figures so we can kind of see the sausage shape. That would be
figure 2, maybe? No. Figure 3? No.
I guess it's figure.
That's figure 4.
Yeah, figure 4.
Figure 4.
The bottom row.
Right.
So these are, this is why it's called sausage, because of this sausage shape in this plane. So the bottom row is showing the VR as a function of V phi. So V phi, the rotation velocity, and VR is the radial velocity. And these are for the 4 models that I'm presenting on the paper, in the paper.
Okay. So
you can see that so these are 3 different models, either with different input physics in the simulations, or with different initial conditions for the dwarf. So, but overall, we can see that all these models, they have this sausage-like shape, which is basically what we observe in the Milky Way for the accreted halo, or the GSE.
Very good. Yeah, that's a nice description of
so the right, so then we know now that there is this main merger event that happened. People are identifying candidates of other accretion events in this chemodynamical space. But then we can wonder, right, so the Gaia sausage Enceladus was a massive merger, and could it have imprinted more than one signature in this chemodynamical space, and maybe we could be misidentified these signatures as a different merger when when it actually happened only one.
Yeah. Okay. I'm with you.
So that was the main idea. And just to finalize in the introduction, we know from cosmological simulations that these kind of mergers of these that are very radially anisotropic, created this very radially anisotropic halo. It's relatively common in Milky Way-like galaxies. So like these Auriga, is it Auriga simulations? About like 1/3 of these Milky Way-like these galaxies, they will have these Gaia sausage Enceladus, or just GSE for short, kind of mergers.
Okay.
So that's the main motivation.
Got it.
And then our group, we start developing this Gastro library, which the name is actually the Gaia Enceladus Sausage Timing Chemistry and Orbit. And the main idea then is also to identify what are the signatures of this merger, not only like in the stellar halo, but also in the disk. Like what does it cause?
Yes. Nice.
And this is mainly also motivated by because one of the facts that we expect to happen when a merger like that happens is that it will hit the disk, hitting in kinematics.
Yes.
So then it will create a population of stars that it has a large radial velocity dispersion as well, which for the Milky Way it was dubbed as the splash. So which is a splash, because when the dwarf came and then merged with the Milky Way, it created this splash component of heated stars.
Got it. Cool. Very good.
But so in a previous work during my PhD, we actually showed that this kind of population, it can also be explained in galaxies in isolation, but during the formation of these galaxies, if in the first giga years they have clumps, which are massive regions of star formation, so that will perturb the disk, and this can also create this splash-like population. So one question that we are interested to understand is also what are the effects if we can disentangle this information of a merger and clumps in the formation of the splash population.
I'm with you. Yep.
But in this paper here, that's the motivation for the Gastro library.
Right.
But in this paper, we are exploring the stellar halo, just the component of stellar halo. So we use this gasoline code with antibody plus SPH code. SPH in the sense then we have star formation, and basically that's there are already studies investigating the effects of a GSE-like merger, but either in a pure antibody model, in the sense that there's no star formation. So we already start with a stellar disk and a satellite that will merge, but you have no gas and no star formation. And and you can also have on the cosmological simulations where you can actually identify Milky Way-like galaxies and see if they had like this sort of mergers. So my models are something in between. So they are tailored simulations in the sense but they have star formation. So we start just with a distribution of dark matter embedded in a hot gas corona.
Right.
And then it will have some initial angular momentum, this hot gas corona, but then it will cool down, collapse, form stars, and then basically start forming your Milky Way-like galaxy.
Yes.
And this we also do and the same is for the dwarf galaxy, that will be our GSE, where it also starts with a distribution of dark matter and a disk-shaped gas distribution, right?
Okay.
So these are the inputs for our models.
Okay.
And then all this transformation happens naturally. The chemical evolution is also just all self-consistent. So it again enables us to, in a very tailored fashion, but we can understand what's the chemical evolution of the galaxy, and what are also the chemical effects because of these Gaia sausages-like merger in the Milky Way.
Okay, so in the SPH calculations, you are tracking along the chemistry, the elemental abundances you go through.
Exactly.
Okay.
We in our case here, we track two elements: the iron, which I will be basically calling metallicity for tracking the abundance of iron, yeah. And also oxygen. And oxygen, it tracks, it's to give an idea of the alpha process elements. So in these models, like the metallicity or the iron abundance, they are very robust. The alphas or the oxygen, they are not exactly the same, for example, as we would observe in the Milky Way, in the sense that like an alpha-rich population, it won't be the same exactly value as an alpha-rich population in the Milky Way. But we can at least distinguish, like we know in the Milky Way there's the alpha poor and alpha rich disk, where the alpha rich disk is thicker compared to the alpha poor. And in our models, we can also distinguish this, like in alpha poor and alpha rich, but the cuts, like what distinguish the alpha rich and alpha poor, they are not the same as in the Milky Way.
Okay.
But qualitatively, it's the same thing. They give the same idea.
Okay, thank you.
Yeah. Right. So then we have. I'm going to be showing in the main paper. We show 4 models. There are 4 additional models in the Appendix B, but we can have a good idea just by seeing these 4 models. And there are 4 models, but so we are investigating 2 initial conditions for 2 dwarfs. So dwarf D1 and dwarf D2, what I will call. And for each of these, we also have different feedback. So that's a supernova feedback. So the amount of energy that when the supernova happens in the simulation, how much of this energy is injected in the interstellar medium.
Right. Okay.
And the idea is also to see if that could cause any effect on these chemodynamical properties of the dwarf.
Okay, and that's on the order of 10 to the 51 are being thrown in.
10 to the 51. Yeah. So FB20 is when 20%. Yeah. So 10% of this 10 to the 51. Yeah. Ergs per second. Yeah.
Okay. Good. I'm with you.
And yes, and so throughout I may be saying either high feedback or low feedback, but when it's low, it's FB20, and high, it's this FB. Oh, sorry. When it's low, it's FB20, and high FB80. Right. Right. And we can now move to figure 1 for instance.
Okay.
Yeah. So all these dwarfs, they are going to happen in a retrograde fashion, in the sense that their orbit will be in the opposite direction as the main rotation of the disk of the Milky Way galaxy in the simulation. It will have a small inclination angle between the plane of the main galaxy with the orbital plane. So this inclination angle is 15 degrees. And this dwarf D1, it's going to be a bit less massive compared to D2. And the merger also happens a bit later. It completes a bit later compared to dwarf D2. So there in figure 1 on the top row, the black lines, it shows the evolution of the center of the mass of the dwarf. So as it approaches closer to the host galaxy. So we just see where it starts, and then at about 1.6 gigayears, it has the first pericenter. We can focus just on first pericenter, then it goes for the apocenter, goes back, has a second pericenter,
Yep, right here.
at around 2.6.
Yep.
Then goes back again for a little apocenter, and then completely merges to the dwarf.
Right.
So basically, in terms of feedback, that doesn't change much for the orbital evolution of the dwarfs. The difference from D1, D2 is that D2 just starts a bit closer, so it merges happens a bit earlier, and it just has
one bang.
basically one clear apocenter after the first percenter, but then it's basically merging with the main galaxy.
Got it.
Another important thing on this figure is the red line,
Yeah.
which shows the label actually for that would be in the last column, but it's okay. It shows this V rot over sigma, which measures the rotation velocity of the dwarf galaxy, and divided by the dispersion of the total velocities of these of the stars in the dwarf.
Got it. I'm with you.
And then it basically is giving an idea of how rotationally supported is your galaxy.
Yes.
And that would be nice actually to see for the D2 models. If you can go to the last two rows. Yes.
Sure.
Thank you.
Yes.
So the one interesting thing is that when the dwarf galaxy is approaching the main galaxy, we can see that if this V rot over sigma is above 1, we can say that the object, in this case the dwarf, is rotationally supported. So we can see that before the first pericenter, in both the high feedback and low feedback, we have that the galaxies, the dwarf galaxies, are rotationally supported.
Yes.
But then after the first pericenter, the one which has higher feedback, it will just become just like a kind of pressure supported.
Correct. Right.
And just decrease. In the case of the low feedback, we can see that after the first pericenter, it will have still a bit more star formation. And that's one of the effects of this being low feedback, because you enhance star formation. So you have that even after the first pericenter, you still have new stars being born, and it kind of recovers a bit the rotation support. But finally, when it's going back to the merger, it will start. It's just basically totally disrupted, and like you don't have any more rotation support. So figure 1 gives this idea of the evolution of the dwarf. The bottom row, it shows also you can have just a broader view of the evolution of the angular momentum, where the solid line is tracking. The solid line tracks the center of the mass of the dwarf, and we can see that basically when the merger completes, the center of the mass will have angular momentum equals 0. Fine. But the median of the distribution of the accreted stars, it will differ depending also on the feedback. Whereas the high feedback ones, it will be, which is tracked by the dashed line.
Right.
We can see that the high feedback ones, they are not going to be exactly as 0. They are going to be, with low, still consider low angular momentum, but not around 0. And the ones with lower feedback, because they have more star formation, so they are become more centrally concentrated. They can go deeper in the potential. So most of the stars, the distribution of the stars will have an angular momentum closer to 0.
Great, got it.
So that's one consequence of these feedbacks in the evolution of the merger.
Got it. Very good. Nice. Very nice.
Right. In table 1, we summarize the properties of each dwarf in the models. So, for example, it's important the mass, for instance. So that's the mass at the time when just immediately before the merger completes. So we can see that these masses they vary a bit, almost 1 order of magnitude, but all of them are within the range of the mass that we expect to the Gaia sausage Enceladus to be. So
okay, good. That's useful.
Yeah, so the median metallicity, and for the metallicity, it's important also to measure, to mention that we are interested in understand the merger qualitatively, so we don't like to exactly match the median distribution or the peak distribution of the dwarf galaxy merging with what we observe. That can be in principle be done, but it's just tweaking how close you start the dwarf in principle, because if you start a bit closer, the merger happens earlier,
Quicker.
and then it doesn't have that enough time for the metal enrichment of the dwarf.
Okay. Mm-hmm.
Yeah, but so ideally we just want to have an overall qualitatively way to understand this merger and what the properties of the GSE dwarf galaxy.
So curiously, the gradient in iron is a lot bigger than the gradient in oxygen.
Yeah, so, and that would be, we can see, for instance, these gradients, and these are going to be very important for the chemical dynamical properties in the later. So these the gradients of metallicity and for the oxygen, these are measured before the dwarf reaches the first pericenter, because when it reaches the pericenter, it will kind of blur things.
Right.
Yeah. So actually, when it after the first pericenters, these gradients, especially in the metallicity, it will become less steep. Okay. So it even gets closer to what observers expect that was the gradient in the GSE dwarf galaxy.
Okay.
So these are the values before the pericenter. So when the dwarf was still not perturbed or stirred by the interaction with the host galaxy.
Thank you.
Yeah. Right. We can move then to the next figure.
Sure, the internal structures, the chemistry.
Yeah, so yeah, the next figure we are going to show, it's the internal structure evolution of the dwarf.
Cool.
The main idea of these, again, it shows we can, for instance, focus just in the D1, so the first two rows. The top row, it shows the circular velocity as a function of radius of the star, so it gives an idea how the matter is distributed in your dwarf galaxy.
Yes,
that's also shown in the second row, which gives the density, the stellar density distribution. And what we can learn from these, for example, if we just see, like, the black one shows the distribution for all the matter. The second row is for dark matter, then gas, and then it starts in the last row. Last column. But the main idea then, it's showing for model D1 for both models where you have low and high feedback.
Right.
D1, like the top row, for instance, if you and the light color. The light color shows what's the distribution before the pericenter. Then what we can see from this is that basically the internal evolution of the dwarf, it's independent of the feedback before the pericenter or the main interaction with the host galaxy. But after the pericenter, we can see that there is a huge difference between high and low feedback. And what's happening is that in the low feedback ones, you have much more star formation, which you can see, for example, in the solid blue line. We have much more star formation. You have much more stars in the center of the galaxy. That makes your dark matter also contract.
Oh, wow. Yeah.
Yeah. And then you can see also, like, in the green lines. And then in the end, so you have...
wow.
Yeah. And then you have that, for instance, the dwarf galaxy, that in the high feedback regime, it will have a more like core-like distribution, something like that. And that shows this the evolution of the internal structure of the dwarf galaxy.
Nice.
we can go for the figure 3.
Sure. Oh, here we go.
Yeah, this one, we'll go back to that later, but for this one, for now, what we can focus is in the first 2 rows.
Okay. If you over
So,
H and O. Okay.
So first 2 rows. So these are a zooming of one of the models, right? And it's showing the stars at time 0.9 gigayears, which is before the first pericenter.
Yes.
Before when the dwarf is still rotationally supported, it's like very well defined, let's say. And then what we can see from there, as it was already shown like in the table, first in the top row, each star is color coded by its metallicity, so we can clearly see the radial metallicity gradient.
Right, definitely.
So for instance, on the left, that's the XY plane.
Huh.
So we can see that in the center, we have the more metal-rich stars. And as you go to the outskirts, you have the more metal poor. And just a different projection in the XZ, and on the right, YZ.
Okay.
In terms of the oxygen, it may seem, given that we saw that the oxygen gradient was very mild, but it seems that the ones in the outskirts are very alpha rich compared to the ones in the center. But if you can see, the bulk in the center is basically kind of uniform. It's just the really stars in the outskirts that are more alpha rich. And this is going to be very important in the later, because the stars that are in the outskirts and that are more metal poor, these are going to be the stars that are first stripped during the merger.
Yes.
So these are the first stripped, and they retain a bit of their angular momentum, and they will end up having more angular momentum, absolute angular momentum, either in the prograde or retrograde direction. We see that in a bit.
Okay.
And before we go, then finally we can the last 2 rows we go back later.
Okay.
This I'm showing the energy. Each star, again, before the first percenter, each star color coded either by the energy that it will have at 10 times equal 10 gigayears. So when the merger already has happened, and when the stars already relaxed, so then we are going to trace then where they end up in the energy angular momentum plane. So from these, we already can have some idea that basically, again, these stars, they are going to, the ones in the outskirts of the dwarf, they are going to end up being the less bound to the galactic potential. So they have higher energy, and they are bluer in this color scheme. And the ones in the core, in the dwarf galaxy, they are going to end up being more bound. And we can already make the connection that, okay, so the ones that are in the outskirts, so they are going to end up being more less bound. And these are the ones also that are more metal poor. And on the bottom, I'm showing it's color coded by the angular momentum they will have again at time equals 10 gigayears. So after after 7 gigayears when the merger completed. So when they start should be relaxed already.
Got it.
And we can see that these stars are going to end up, the ones in the outskirts, these are the ones that end up having more absolute angular momentum, either in the prograde direction, red, like being positive there, or negative, more negative being bluer there. So we can already we can actually then jump for that plot, because we can see, we can already predict that, okay, so the stars that are in a Gaia sausage-like merger that are more metal poor, these are the ones that naturally end being less bound and with a higher absolute angular momentum. And that will be very important to try for trying to identify substructures in the Milky Way, and like to see, okay, are these substructures really coming from different mergers, or can they be explained just by one single merger?
Okay.
And then we can then basically then skip to figure 5, I guess.
Let's go
for a while.
5. Oh, continents. Okay.
Yeah.
Okay.
So
got here.
So
Bridge.
okay, on the left, I'm showing data from apogee data for the Milky Way. So that's observational data.
Okay.
I'm using the same color scheme that I use for the models, just for reference. So it may seem that in this particular part that may seem that it's not so very well substructured, but it's just to have some illustration. But because if you are interested to identify substructures in this in the Milky Way, you not only use the energy and momentum in metallicity plane, but other variables like the actions, like the JR, JZ actions.
Action
So yeah. So here, for the models, we can see, as I was saying, that we can focus on just one because they both basically show the same trend.
Yes.
Where the metal-rich stars
are
going to be the ones that end up at angular momentum closer to 0. So that's the reddish color, like center at around 0. And these are the ones that are going to be more bound to the potential, so having lower energy. And towards the higher energy or the stars that are less bound, these are going to be the more metal poor and having either more retrograde or more prograde orbits. And why this is important? So, for example, it's discussed in the paper that, for example, there is one substructure that's called Sequoia, which was in the Milky Way. It was identified as possibly another merger that happened in our galaxy. And these stars that are main candidates to be members of Sequoia, they are on they have very low angular momentum, so they have LZs lower than these. These values of angular momentum, they are normalized by 1000. So it's not minus 2.5, it's like minus 2500.
Right.
So
right.
So the Sequoia would be on very retrograde orbits, so they would have high absolute LZ, but on the retrograde part. They also are identified as being less bound to the potential, and the observation shows that these stars are more metal poor compared to Gaia-associated-like stars. So then, because Sequoia, so it is more retrograde, has higher energy, and it's more metal poor. So, you can say, it's completely different from what we observe from the GSE. But actually, a merger like GSE can naturally explain a substructure like Sequoia. Because as it shows there that when this massive galaxy comes, the stars are going to be distributed all over the LZ energy plane. And depending, and also it will be also correlated with their metallicity. So like a Sequoia region, for instance, would be a bit on the left on the dashed lines on the top row.
Right.
And we can see that all the models show that these are like more metal poor overall.
Right. What are the cyan bluey colors?
The cyan blue, these are tracing the old stellar disk. So the stars that were in the host galaxy, in the Milky Way-like galaxy, when the merger happened.
Got it.
So these are, and this is to illustrate, for that will be explored in a future work, that the importance, for instance, for the feedback. So if we see the second and third columns, which are just differing by feedback, we can see that the cyan colors in the high feedback ones, they are very narrow.
Right.
So, and if they are very narrow, so which means that you don't create too many retrograde stars only with the merger.
Mm-hmm.
And in the low feedback ones, we can see that the cyan lines, they go a bit to the low angular momentum and also to less bound energies. And the low feedback ones are the ones where the host galaxy will have clumps.
Yeah.
So if you remember what I mentioned in the beginning, so the clumps are important for the splash population.
Yes.
So the cyan colors is kind of tracing the splash, and it's already kind of, this is like a spoiler for the that's
okay, I'm with
that in order like to have a splash like population, you also do need clumps and the merger to be in place, you know.
Right.
Like only as Gaia sausage like merger, it wouldn't have a significant splash population.
Right. I'm with you. Got it.
Yeah.
Very cool.
Right. On this, in the second row, it's showing the dispersion of metallicity in each beam. Yeah, we can. Oh, that would be the second row actually. That I mentioned.
Okay, so second row.
Yeah. So the second row should.
Okay.
Yeah, I'm sorry. Yeah. So the dispersion of metallicity in each pixel, and again showing that for the low feedback ones, you have a higher dispersion. That's not exactly what we see in the Milky Way. But again, it's the main idea is to have some qualitatively idea of the merger. And finally, also on the third row, the bottom row, it shows the MDF for the accreted stars as the solid lines, the black solid line, sorry. And the yellow line, it shows the distribution of Milky Way observational data that was taken from the H3 survey, which is a survey that a spectroscopic survey to measure radio velocities and metallicities for like halo, mostly of the halo stars. And we can see that again, the peak metallicity in our models, they are overall more metal rich compared to what's observed in the Milky Way. But again, like these can be fine-tuned, just, you know, if you make the merger happens a bit earlier, then basically the peak metallicity will be comparable.
Correct.
Yeah, and the other important thing is the dashed lines, which shows the MDF for these very retrograde and high energy population, which would be like something like Sequoia for the Milky Way. And also to give an idea that these stars, they have a more metal poor distribution compared to what is to the overall distribution of the GSE.
Yes.
Yeah. So from these already, like in this from this figure, we can already like we can try to it's another way to understand like something like Sequoia that people argue as a distinct merger, but like we know that the GSE merger happened. What are their properties? So, and such merger can naturally produce something like Sequoia. And one thing that also that the observations show, like the different groups, they show that it's not very clear, for instance, the alpha abundance of Sequoia, if it's in the more alpha rich or alpha poor regime. But this, for example, we can go back to figure 4. And figure 4 on top row, it shows the alpha iron plane. So the metallicity as a function of the oxygen. We can focus on it shows the overall distribution for all the stars on the merger, but we can focus on the pink lines, on the magenta, on the magenta scatter points.
Yes. And
these are the stars that are on very retrograde orbits that have LZ lower than -1500. So
Right.
that would be like the Sequoia-like. And we can see that they spread all over the alpha iron plane, which means that, you know, you can, a Sequoia population, it can, even if, depending on how you observe, you can either be selecting just the alpha rich or the alpha poor, but overall, a Sequoia population will be characterized by being spread all over this alpha iron plane.
Yeah.
So,
yeah. Cool.
right.
Nice.
Okay. Yeah. So that was one main takeaway. Second part, like for instance, if we go to figure 6.
Figure 6, eccentricities.
Yeah. Again, on the top row, it shows again for the models and for the Milky Way on the left, for accreted candidate stars. It's color coded on this plot by metallicity, and again we can see so it's the angular momentum as a function of eccentricity. We can see again, so the stars that have centered on LZ equals 0, they're going to be more metal rich. We already seen that. But overall, so the eccentricity distribution of these stars, they are mainly very high on very eccentric orbits.
Yes.
Like these contours go very, very deep, but in the histograms is a bit more, it's also kind of clear.
Oh yeah.
That they basically, it has a sharp drop for eccentricity lower than 0.7. And another thing, but it's already kind of, you know, it's kind of obvious, like if you select stars that have more absolute angular momentum, because you have more absolute angular momentum, they are going to be on relatively less eccentric orbits. So that's just showing that, okay, Sequoia-like stars, you already expect them to be on less eccentric orbits, which is given by the dashed lines. And one interesting thing also to compare with observations, and each model basically, depending on the dwarf and also feedback, it has different properties. So it's the relation between eccentricity and metallicity. So for the Milky Way, we can see that the blue line corresponds to the prograde ones, and the red ones to the retrograde ones in the Milky Way. This was distinguished because originally, when that plot was first shown in Cordopatis 2020, the authors they you know, for you to select an accreted population, it's not so trivial. So they basically consider stars that are on retrograde orbits to be accreted ones. So, but now, because in the way I selected accreted candidate stars in the Milky Way, using also chemistry, I can do like for prograde and retrograde stars. And basically they show the same trend as it was already known and shown. And we can see that in the models. So we say for the Milky Way that the eccentricity increase with metallicity, and except for this, the third row for the FB20D1, which basically flat, like there is no relation. But overall, we can, the models show that there is a qualitatively similar relation as in the Milky Way, in the sense that eccentricity increase with metallicity, with the difference that in the low feedback ones, the high feedback ones, you have this turnover. And that, which is not actually observed in the Milky Way. So so looking to these in different planes, also can try to to select what would be the best model to represent the GSE merger.
Yeah, it makes sense because we're all out there. Okay. Yep.
Right. We can go to the figure 7.
Yeah, it's all set up. Okay, figure 7, implications, Gaia, action space, action angle.
Yeah, and this is also very important for when trying to identify different substructures in the stellar halo of the Milky Way. Because one, again, as I mentioned in the beginning, one way to try to identify these substructures is looking this action angle space in the actions. So JR, which gives an idea of how radially extended is the orbit of the star. JZ, how vertically extended it is. And J phi, which is basically the same as the angular momentum, LZ. And so when you try to use some algorithm to identify substructures in this space, you generally use JZ, JR, J phi, or angular momentum, and metallicity. And what's actually showing here, it's showing that in the JR, we can focus on the histograms. I guess it's the JR, for these GSE-like mergers, it spreads over a large range. So going, depending on the model, from 0 to over 3,000 in JR. So it spreads over a large range. And whereas in JZ, it's very concentrated. Its distribution is very narrow. It's basically goes up the vast majority goes up to 500 or not more than 1,000.
A lot more.
And this is just because of the nature of the inclination of the satellite during the merger. So that's why the stars will end up with a low, relative low JZ. And why this is important, for example, in the implications. So there is one subsection called to a cautionary tale for the other substructures.
Sure, cautionary tales. Beware, cautionary approach.
Yeah, a cautionary approach. So there have been, for example, a few substructures that were identified, again, in this action space. And for example,
okay, just refreshing.
Okay, yeah.
Good.
So there were a few substructures that were identified, but for example, and there was this particular substructure called Pontus, where it will have an angular momentum closer to 0, low JZ, lower than 500, and also it would be the difference between the JR of Pontus with the GSE of the Gaia sausage Enceladus is lower than 1,000 kpc, kilometers per second. And if we refresh our minds on that plot, so basically this difference in JR around 1,000, it's basically it's where you can 1,000. It's not a huge difference between two substructures. So Pontus is also something that can be naturally explained with a GSE-like merger. And moreover, the metallicity distribution of Pontus, it's very similar or very close to the Gaia sausage Enceladus. Both Pontus have low JZ with GSE, as we show, also have low JZ, but the JR of Pontus, it's within the range that we already expect the Gaia sausage-like merger to happen.
Okay, cool.
And we can also extend this kind of interpretation, and because there is two other two substructures, one called this LMS1 or Wukong, and that was also identified. And hold on a minute, and the other one that was identified is Cetus. So this LMS1 and Cetus, which are also identified as distinct substructures, they have a high JZ. So okay, they are not explained by the GSE models. That's fine, but again, the distance in the JR in LZ of these Pontus and of Cetus and LMS1, they are very close, and they can also be, using the same line of reasoning, they can be explained also by a single merger, given that they also have the same metallicity distribution.
Right. Okay. So these are classes.
Yeah. So, it's these things are very interesting, you know, trying to applying algorithms to try to find substructures. That's very important to see. But
Good.
it's need to be to take in consideration what are the expectations from simulations on this aspect. And you know, you don't need to invoke several mergers to identify the substructures when there is this massive merger that happening in our galaxy. And this is also motivated because, for example, in cosmological simulations, it is expected that the inner stellar halo of a Milky Way-like galaxy, it's actually made up to 2 or 3 maximum mergers. So if you start seeing too many mergers within too close in Milky Way, that's already not what's predicted or expected in the cosmological context. So you expect to, of course, in the outer halo, you expect to see more of these minor mergers.
Cool.
So that's the main I guess I explored the main takeaways from this paper. So the main takeaway message is that a GSE-like merger can naturally explain some of the substructures we already know, like the sequoia. We can also try to understand other substructures in the sense that if they are too close in the dynamical space and they potentially are also part of some same merger. And one interesting thing is also that we also predict the presence of these prograde substructures because when I was talking, I didn't mention that much, but the merger will also leave some imprint in the prograde part of the stellar halo. And these are also going to be like more metal poor on relative lower eccentricities. And there is actually one substructure that was identified, this Candy 14 or DTG2 by Myong and Yuan, where potentially they can also be explained as coming from the GSE merger.
Yeah, very nice. Cool. Awesome. João, thank you for walking us through your very lovely article.
Yeah, thank you.
Yeah, very good. Where's my the Gastro one? Very cool. So let me ask you, where do you think we go with this topic over, let's say, the next 2 to 5 years? I noticed this is Gastro 1, so maybe there's a Gastro 2 or possibly even a Gastro 3.
Yeah, so
5, 6. Is there additional data coming from Gaia that can help identify some of these other splash structures or non-splash structures, as the case may be? Is there other theoretical, or is there new models that can be done, that kind of stuff? So where do we go over the next couple of years?
So yes, the idea is to now to explore the effects on the disk of these Gaia-associated-like mergers. Also, not only on the disk, but also in the bulge region, like the inner parts of our galaxy, and what can be the effects of that. Yes, recently we had the Gaia data release 3, which also improve give much more data to be explored and trying to find these substructures. But now also with taking consideration now that, you know, even if you identify one of these new substructure, how statistically significant it can be from not being part of the GSE-like merger, for instance. And Gaia will still be going until Gaia data release 4, which also improve more the parallax and proper motion. So yeah, probably more substructures are going to be identified and being able to narrow down these. Another idea for the future years also is to have these runs in a higher resolution mass resolution. So to be able to see in very tiny details the stripping process of the dwarf galaxy merger, and also the effects on the disks and what are the dynamical signatures on the disk.
So what was the mass resolution on the ones in the article? What was that roughly?
10 to the stellar mass is 10 to the 5.
Okay. Okay. Yeah. So if you can get it down to 10 to the 4.
Yeah.
That'd be great. Yeah.
Yeah.
Cool. Nice. Well,
Yeah.
I look forward to seeing many splashy events coming from this body of work over the next couple of years. It'll be really great to help disentangle.
Okay.
Very
okay.
cool. Very nice.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better, and we will see you on the next one. Bye-bye.